3, anything that you are not sure? Yeah. All right. Now today we look at power. What is power? Power is take your work divide by time. You take your work divide by time. What is work? Work is force and the displacement. And now you learn something new today, which is called power. Power, you take work divided by time. Not divide lah. You integrate with time. Time interval of your time. Okay. So you know that your work is force multiply or dot product of your displacement. So when you put your equation du over dt with this form, you can pull your F out. Because normally, previously, your force is constant. But you have seen that force also changing when you have force equal to some equation. But we can pull our force out, and then we have dr over dt. dr dt is a velocity. Okay, dr dt is a velocity. So power also force multiplied by velocity. Okay. What is the unit of power? Watt. Okay, it's a watt, W-A-T-T, or unit SI. Force is a Newton. Velocity is meter over second. So it's also Newton meter over second. It's the same. Sometimes you link with Joule also. So you know that previously when you learn about work, Newton meter also equal to Joule. So there are 3 units for power, either in watt, capital W, or Joule over second, or Newton meter per second. Next, when you deal with power, you deal with efficiency. Efficiency, very easy principle. You take your output divided by input. Okay. So in this case, we use power, your output power divided by input. Okay, you can use your work output also divided by work input. Okay. So in this case, we use power. You can use energy, because power also in joule over something. Right? What is important is that you take output divided by input. What you give up divided by what is your input. Let's look at how we apply the principle, not the understanding in power. So this question, you have a man push 50-kilogram crane or object with a force 150 Newton. And you look carefully on the diagram, this force is not straight line. It's not a normal horizontal force, but with an angle, right? And it gives you a normal triangular relationship, which is 5, 3, and 4. Okay. Determine the power supplied by the man when t equal to 4 seconds. So again, recall what is power. Power is work divided by time. Your time is given now. You need to find work. It is you recall back what you learned previously for work. Definition for work again, force multiplied by displacement. And you get positive vector, positive work means both vector are the same direction. And both force must be parallel to give you work. Okay. So coefficient friction was given. So it just gives you a hint that you need to find the normal force. Because from normal force, you can convert into friction force. Initially, crane is at rest. You are given the initial velocity. Okay. So how do you solve this question? So in this case, you can solve by chapter 2, F equal to ma, or if the question asks you or instruct you to use principle of work and energy, then no choice. You have to use principle work of energy. In this case, Most of the time we use chapter 3 equation, which is principle of work and energy, because it gives you faster calculation. Because here it gives you friction, it gives you time, and the question gives you power also. Ask you to find power. Definition power is work divided by differentiate with time. So basically, you straight away use chapter 3 principle of work and energy, you will solve this question. Okay. All right. So free body diagram, I draw. So first you have work, you have contact surface, you have Newton, and you have friction. Friction is the opposite direction of the motion. In this case, we predict the motion will move to the right. So the motion is opposite. So it moves to the left. What else is missing in a free body diagram? The force. So include the force. How you draw the force? Normally, I will recommend you go through, the force will go through the center of the object. Right? So from chapter 3 onwards, I will highly recommend to focus all the force through the center of mass or center of gravity. Right? Well, you can draw some axis from the center, and then all the force will go through there. Okay. And for the motion, we overlap the kinetics diagram on the same free body diagram. So we assume the acceleration will go to the right. Based on the force direction or vector direction, we assume all the positive acceleration to the right will give you positive value. All right, then you solve. Then you solve. You solve by looking at two directions. One is to the left, one to the right, one go upwards, okay? Or x direction or y direction. So you split chapter 2 question F equal to MA. In this case, you look at y direction. You split all the force into y direction. So in y direction, friction cannot be counted because friction is not y direction. Unless the surface is slanted at a certain degree, then you have friction force. In this case, the floor is flat, so you don't have friction force in y direction. Okay, so you can understand, right? So you sum up all the force equal to ma, and in this case, acceleration in y direction is 0 because the object do not move up, it moves to the right. Okay, so here is a simple logic. So some of the student you might confuse and you might stop here. You don't know what is y. Okay, so look carefully. From the first equation, you can calculate or determine the n normal force equal to something. Then you calculate for the y, for the x direction also. You will find the unknown, which is the a is missing. Okay. So far, everything makes sense to you? Try to understand the way we solve. What equation or what are the ways that we need to be careful, right? And those, if you're weak in trigonometry, go home and practice your trigonometry, tangent, sine, cos. Okay. So you have your normal and acceleration now already. You call, in this case, because your acceleration is constant, so you can use the motion equation. In this case, we use v equal to v naught plus at. Initial 0, we want to find the velocity at the end of the action. Why? Because power also equal to force multiplied by velocity vector. Okay, power have two definition. One definition. One is the change of your work, or it is the vector F multiplied by vector V, FV. So we have two. So that's why we get V vector equal to 0.12 meter per second. Although here do not give you the direction, when you get positive, you need to understand, in this case, your V is moving to the right because your kinetic diagram show you where is the positive direction. Your kinetic tell you that your A is moved to the right. So A link with the velocity, same direction. Okay. So the power, straight away you use F dot V to get, in this case, in X direction. In X direction, you take the F direction, multiply by the V. Again, here we are dealing vector. When you use dot products that link to the vector, they must be go parallel. That's why here you see we take the F direction rather than the Y direction, because Y and V, they are 90 degree. 90-degree vector give you 0. Okay, 90 degree give you 0. Or in vector form, you take ijk, you take I multiply by j, you get 0. You only get I multiply I, you get 1. Right? So same with this case. You substitute, you get your power. Remember the unit is watt or joule per second or Newton meter per second. Okay, so this is how you solve it, by straight away applying the definition of power, F multiplied by V. Okay. Okay. Next example, which is you might be applying this one when you work in the industry. So you have a pulley system that activated by a motor. So motor, you know, when you buy a motor out there, you need to tell the boss, I want to get a motor in how many watt or how many volt and so on. So you need to know a little bit on energy that can created by this motor. The motor M, it hoists a lift. You want to lift an object of 35 kilogram of this crane, so that the acceleration at point P is this one. The point P means the rope that pulled by the motor here, you can move in the, I think there is a mistake here. Acceleration was given, but the unit, the 2 is missing. It should be meter over second square. So this is not, this is velocity, but the question gives you acceleration. So the unit is wrong. Determine the power that must be supplied to the motor at the instant P has velocity 0.6. You're given acceleration at point P, you're given velocity that you need to find 0.6. Ignore mass of the pulley, cable, and take. This one is what? This is efficiency. Okay, efficiency equal to 85%. Recall the definition of efficiency, power output divided by power input. In your answer, you write this one out, you get 2 marks for definition of efficiency. Okay. So when it comes to your assessment, every time you write a general equation to define that parameter, you will get marks for that. First, you draw free body diagram. So before you draw free diagram, you're actually dealing with pulley system. So pulley system, you look at the datum, you look at where is positive, where is negative. In this case, datum positive go down, and P going horizontal. SP going horizontal. So actually, you have 2 different directions now. Okay. So here, again, you need to find the relationship between your C and P. You find the total length first. Total length, you differentiate by time. You will get the relationship between the speed of C and the speed of P. You differentiate one time, you get acceleration of C and P. You get one set answer there. Then you continue with your chapter 3 solution. You draw free body diagram of your C. So your weight always go down. In this case, there's no contact surface, but there is a cable or there is a something pulling the C go up. So there's a force pulling up. Right? In this case, the force I put 2 cable here, which is two tension cable. pulling the object. Okay, you have seen this one in the, I think in chapter 2, one of our example. Okay, so in this case, we follow the datum direction, go down positive. Okay, follow the datum, go down positive. In this case, there's no contact surface, so there's no normal force. Right, and in this case, resistance of air was not given, so you don't need to consider the resistance. You overlap your kinetic diagram on the same free body diagram. Acceleration go down. Why acceleration go down? Because we want to align with the datum direction. Although it might go up, but we follow the datum. So datum go down, acceleration go down, y positive go down. Okay. Okay. Then you use F equal to ma in y direction. You can find the acceleration of your c. Right? So here, you on the left-hand side, you balance all the force in vertical direction, which is why go down positive, equal to ma. Here, your focus on object C. Right? So it will give you the first equation. You can calculate the weight by mg. M is given 35 kilogram. Look carefully when it comes to assessment. Most of the time, we will not give you kilogram, we will give you megagram. So change the weight into kilogram. Okay. So to get the first one, so again, the next one is to link C and M with using the relative motion or the rope, the pulley system. So you pull, calculate the total length. Total length, you get 2 SC plus the SP. Right? So you differentiate, you get the acceleration, velocity and acceleration. In this case, 0 equal to 2 AC plus AP. So you get the relationship between AC and AP. Right? So in this case, what does it mean? AC equal to minus half AP means that C go down, AP will go to the left because you get negative, means you look at the datum for P, positive go to the right. But here you get negative, it means that when C go down, your P will move to the left. Okay, move to the left, and also it will slow down also. Acceleration also means deceleration. Okay, you substitute the value for P because in the question you want to focus on an individual point, which is at the acceleration when it's 1.2 meter over second square. Again, there's a typo mistake in the example 7. This is 1.2 is acceleration, not velocity. So you get AC, you substitute back to the equation 1 in the question. When you substitute back, you get the tension over here. You get the tension cable, the force of the thing. Okay. So you slowly solve for the question already. So definition of power equal to force multiplied by velocity. Force in here, the power here is linked to the machine here and not object C anymore. Here, because of the machine motor here equal to force multiplied by velocity. Velocity here is the velocity of P here. Okay, the force that linked to this P force here is actually one of the cable here. So just now you find the T already. You find the weight and balance out, you get 2T, you divide 2, you get the tension cable value, and you know the velocity was given is 0.6 at P cable here. You substitute inside, you get the power for the machine, 109 Newton meter over second. But it asks you to power must be supplied to the motor. This is the power 109 This 109 is a power that you need to pull the object. But if you do not supply enough, because of your motor only can supply 83%. So you need to supply more power. The question asks you, what is the supplied power needed in this case, so that you can pull the 35 kilogram object. So recall the definition of efficiency, which is power output equal to input. You have the output. You have the output. You want to find input, move this one, efficiency, move down. You can find your input. Okay. So from the calculation, energy input is 129 watt. Okay. So recall definition, move here and there, you get the answer. Okay. Okay. Example 6 and example 7 is focusing on the direct application of P multiplied by V. Again, don't forget that P actually have another way of defining it. It is the change of work divided divided by time, right? Work towards time. So example 6 and 7 is direct application. Next, we will look at conservation of force and potential energy. When we talk about conservation of force, or the question purposely mention this keyword, considered conservation of force in your calculation, it means that your work and force is independent of path, meaning it doesn't look at whether it's a linear path or curvilinear motion. It's only focusing on the force position. What happened before and after. Focus on the force only. So example, there are two types of force that deal with conservation of force. One is falling object, or the bullet or rocket shooting up, that it doesn't contact with any ground. So weight of the particle, which is your W always pointing down. So that is conservation of force. Another one is the spring, right? If you have a spring, you pull, the spring will always move up and down, and there's a oscillation on that. So that is conservation of force that you can apply when you have these two scenarios. Okay. What doesn't meet with conservation of force? Which is friction force. Friction force is another example where it cannot fall under conservation of force, because the work done by friction force depend on the path. The longer you go, the longer work that you do. So it doesn't do this one. So again, friction force is there, non-conservative. So since we deal with conservative of force with the falling object, we start to introduce you gravitational potential energy. Previously, we introduced you kinetic energy, which is, you can say, non-conservative. But when you talk about potential energy, then it's fall under conservative force and potential energy. So when you're given a datum, let's say you look at this diagram, you have 3 points there. Your datum is at the center of the position. If the object is above datum, your weight will be positive. If your sorry, it's not weight positive. Is the energy that you get is positive. If the object is below datum, your potential energy will become negative because of the Y position. Okay. You know potential energy equal to mgh. The H need to refer to datum. In chapter 3, when you deal with potential energy, in previous physics module, you don't need to consider datum. But when it comes to engineering dynamics, we always refer to a position, a reference point. So in this case, your datum will give you either you have a positive potential energy or negative potential energy, referring to datum. Those that above datum will give you, means your starting location is above datum, means it give you potential energy. If the starting object is below the datum, then it give you negative potential energy. Next, spring. Potential energy of spring also give you potential energy. So the first one is unstretched. Unstretched means you don't have any energy on the spring. You see the second diagram. If you pull the spring, the position or displacement is positive from the reference datum here. From the unstretched position, you will get positive potential energy for the spring. You will charge up the spring. On the other hand, third diagram, you compress the S also positive, means there is a negative also. But you know that negative, when you calculate the energy is Ks square. The S is negative, but square you still get positive. So for spring, it's a special case. You will always get positive energy for spring. Okay. So new equation for spring. Energy for spring will be half kx squared. Okay. So there are two cases we discussed just now. Potential energy, when there's a gravitational force, there's a datum given, your mgy or mgh. Above you get positive, below datum you get negative energy. On a spring, you always get positive. The formula to calculate the energy for spring will be half kx squared. So when you combine these two cases together, where we consider potential energy and spring energy, then you get total energy, gravitational Vg plus Ve, elastic force. Okay. So there is a work done if you have do these two systems. So you will take energy 1 plus energy 2. Energy 1, energy 2. We look at example. So if you have a spring combined with the object that pulled by the gravitational force, you are given a datum. You look at this diagram, datum is above the object. It will give you negative potential energy for the object here. Okay, so be careful on the datum. So that's why you see here, your gravitational force is negative. It's a mgh, right? It's a mgh, ws, s is negative. Right. Then spring, elastic energy will be half kx squared or ks squared. See, all right. Just need to highlight, focus on the datum for the potential energy. So if you want to find the work is the differences of energy happen between the two positions. In this case, you take position 1 minus position 2, you get this equation. You take position 1 minus position 2, and not position 2 minus position 1. You'll get one equation. So we start to do a bit derivation. So let's say you have one particle move from bottom to top. Bottom, you have three-dimensional location, x, y, z. Top one, there's a change of x, change of y, change of z. So you have three location change. Work done, the work of W and the force will give you U 1 to 2 equal to energy, potential energy 1 minus potential energy number 2. You can rewrite the above equation with du equal to the change of energy, potential energy. Here you have two. One is before with its x, y, z, and the second location, bracket, second location. Mathematics, you can rewrite like this. In vector form, you change what you learned before this. Energy, not energy, work equal to force multiplied by displacement. Your force now is in I, J, and K. Your position or displacement also in I, J, and K, but there's a change of X, change of Y, change of K. As you learn, there's a dot product. I times I, you get value. I times J, you get 0. I times K, you get 0. So you only have three value after the multiplication or your dot products. So you get fx dx plus fy plus z dz. All right. Then you express in the differential dv. This one expressed in terms of dv. So fx dx fy dy fz dz equal to minus v x dx. This is a partial differential, but we're not interested in this one. It just let you know that you can write all these terms in fx minus partial differential v dx and so on. Right. Okay. These slides we start to we will not use this one in this module, but when you see partial differential xi, there's an inverted triangular. This symbol, you will see this one when you learn about finite element analysis in your final year subject, nervous stroke equation and all this. Okay, so just introduce you the new symbol, inverted triangular. It means partial differential of your I identity vector Z and K. Okay, they are called vector operation. You will see this one in a high level calculation. For example, Gauss equation, fluid dynamics, and all this. After all this derivation, only one you want to focus on will be this one. You know that you previously you learned about principal work and energy. When principal work and energy, if you see this one, is that you combine with the conservative and non-conservative force. You can write kinetic energy plus V is your potential energy. Work done by non-conservative because here you involve with friction and other forces, right? Then the right-hand side is the kinetic energy and the potential energy. If the question asks you, consider only conservative force on the work, you cancel the middle one, the work for non-conservative. Your equation will arrive just like this. You only look at what changes to the kinetic and potential. So kinetic before must balance with all the kinetic plus all the potential at the end of the station. This equation is called equation conservation of mechanical energy or conservation of energy. Yeah, so new equation. Conservation of energy, you deal with energy. So you only have two types of energy so far, kinetic energy and potential energy. You balance the two energy. Before must be equal to the total after. Okay, this is deal with energy only. Don't confuse with principle of work and energy. Don't confuse with these two equations. Right? So this is a bit more information for you guys. Those playing basketball, you see the datum. Datum is above the horizon. If the ball fall from above the datum, but the potential energy is positive, then at the half, you get half the potential energy, but another one is you have a kinetic energy. Then when at the bottom, your kinetic become maximum potential 0. Okay, this one you're very familiar in your physics, right? Changes between potential and energy, potential and kinetic energy. All right. So this is just a derivation, what happened from the top and bottom. So initial one, you get your total energy for V1, T1, V1. You will get E equal to 0 plus WH or MGH. Right? The top one don't have kinetic energy. But you want to prove this conservation energy equation. So how do you prove at the middle? So when you want to find in the middle, you need kinetic energy, you need mv squared, you need velocity. So how you find velocity? In this case, what is constant? Acceleration is constant because gravitational acceleration is constant. You use v squared plus v naught squared plus ac y minus y 0. You will arrive at one velocity with the square root of gh. You put inside the kinetic, the conservation energy equation. So your energy at the middle point here will be half mv squared plus mgh. Your h now is half, right? So you substitute the value here, half mg squared. The m you can find from the weight divided by gravity. This slide just show you that sometimes questions do not directly give you the mass of the object. It straight away give you the weight of the object. Look carefully. Mass is in kilogram. If the question give you the weight of the object in Newton, then it expect you to convert W divided by G, you get back mass. Okay. So when you see the question give you object in weight Newton, then you actually can use this equation to solve, to find the kinetic energy, the M here. Okay. Look carefully. So here you balance up, you still get WH. The energy is still the same, no matter where is the location, either on top or bottom. Right. The rest is just a proving of the conservation energy equation. Even at the bottom, you still get WH. The total energy equal to WH. Okay. Okay, so this is the general equation when we use, if the question purposely asks you use the conservation of energy, we just want you to add the sum of symbol inside the equation. Sum of kinetic energy plus sum of potential energy before equal to sum of after. Okay. Can you go one more? Then we break. Yeah. We look at this example number 8. Yeah. So you have an experiment when you want to test the aircraft design. So what you do, you hang the aircraft at a certain distance with the datum here, and there's a rope of 20 meter per meter, 20 meter, and there's a rope here AC. There's a weight of this aircraft, a body, and there's an angle there. So this is called Grand 3 structure. Okay. So you want to see the response of aircraft during a crash, so there must be something happen at the below. The plane having a mass of 8 megagram will hoist back until angle equal to 60 degree. Then the pullback cable AC is released when the plane is rest. Determine the speed of plane just before it crashes. We want to find the velocity at B. On the ground, theta equal to 15 degree. Means the aircraft start from 60. When it reaches 15 degree, the aircraft crash or it stop. Velocity here is 0. Also, what is the maximum tension developed in supporting the cable during the motion? We want to find the tension cable here, the force. Ignore the size of the plane, effect of lift caused by the wing during the motion. Right. Before you go inside there, you think logically. When you cut this AC cable, what is the motion of the aircraft? Is this linear or collinear motion? Collinear motion, not linear, because this one tied to a cable. So tied to a cable, it will swing in a collinear motion. Collinear motion, think back, what do? You need normal tangent, and then call back the acceleration equation. Acceleration, you can break into two components, normal and tangent component. What is the equation for normal acceleration? V square over rho. What is the AT? V dot or differentiation of the velocity in tangent direction. There is an equation to calculate this one. All right, 1 plus something, but in this case, your rho is given, so you don't need to find. The rho is 20. Table fixed. Okay, so you draw the free body diagram. Put in normal tangent, normal pull up because the curve is pointing up. Tangent because the aircraft is going down, so tangent direction there. Then you start to put into all the force you have there. Here we don't have engine, the engine doesn't start, so there's no force pushing the aircraft down, only the inertia from the mass. So at a certain angle, at 60 angle or 60 degree, before it cut the cable, weight is pulling down, and there's a tension cable on the body of the aircraft. So don't forget to observe the scenario. So when you do free body diagram, is something attached, then there is something there. Because when you come to chapter 4, chapter 5, when you learn about momentum later, some of you forget that actually there's a force when you attach to the body. Okay, in this case, cable. Then angle will be 15 degree from this location. This one is when it hit the ground. All right, 15 degree. So potential energy, you use conservation of energy. Right, conservation of energy at point A will be equal to point B. So energy at point A was same as energy at point B. So we only consider two types of energy, potential and kinetic. So for A, you put in kinetic equal to half mv square, V equal to mgh or wh. Same with the other side, before equal to after. Then be careful, the datum is positive, go down. When the positive is go down, so be careful on the negative sign. Especially you see the potential energy for A. A is negative, not positive, because it's below the datum. the HA here. HA, you need to calculate. There is a 20 meter, there's an angle, you can find the H from the datum. Same with B. B, your kinetic energy at B also negative. Sorry, potential energy also negative because it's below datum. Be careful, positive, negative sign. You put in all the value. There's one more missing, which is V. Your velocity at V is missing. Okay. Find your B, you substitute back. Equation of motion, again, F equal to ma. You find for the tension cable here, F equal to F equal to ma and normal direction. You find the T tension because the question asks you the tension. So you only focus on normal direction. You balance the force here. Again, A acceleration in normal direction, you can calculate with the V square divided by rho. Substitute, you get tension. Okay. After break, we will look at example 9. We are interested in the position B angle was given here. Yeah, here is 15 degree. Here. The angle 15 degree is here. Before crash. You have two angles. One is before you cut the rope is 60. The question asks you what happened when it reached ground here, 15 degree here. You need to break. You draw triangular and then you shift here and there. Okay, later I can explain to you. Wait, I stop the recording first.